Today we're going to expand on our factoring skills and begin factoring expressions when a equals 1. So why is a equals 1 important? Well, because a equals 1 comes from the standard form of a quadratic equation. We're going to, for the most part, be factoring quadratics today. Standard form of a quadratic equation was ax squared plus bx plus c. We added an equals 0 on the end to make it an equation, but today we're just going to leave it as an expression. The leading coefficient named a will always be 1 in this section. And if there's ever an exception to that rule, we're going to be able to find a common factor to pull out front to make that leading coefficient 1. So before we do all of that, let's do a quick warm-up. Let's go back and remember how to multiply two binomials together. So remember, this was a big distribution problem. I had to distribute the x, then I had to distribute the 5. In doing that, I multiplied the two first terms of each binomial together. Then we multiplied the outside terms. Then I had to distribute the 5, so I multiplied the inside terms and the two last terms of each binomial. Notice the 4 words that I used to describe our distribution process. These words actually have a special meaning in math, and we have an acronym that we call it named FOIL. You've probably heard of it before. I'm pretty sure your parents have heard of this many, many times, but FOIL is usually what this process is called. When I use FOIL, then remember I combine like terms and I end up with a quadratic trinomial. It's quadratic because it's got a highest power of 2, or in other words an x squared, and it's a trinomial since it has 3 terms. When I use FOIL, it does create a quadratic, and that's what we're factoring today. Earlier this year, we did some factoring. You've actually already factored a few quadratics before. What we were actually doing was reversing the FOIL process. So look what happens when I reverse those two portions of our multiplication. We were able to, earlier this year, go from this quadratic to its 2 binomial factors. We found numbers that multiplied to 15 and added to 8 and put those into 2 binomials, but really what we were doing was reversing our multiplication. So what if I multiply these 2 binomials together? Notice that they're almost identical, except that one has a plus and one has a minus. Let's take a look and see what happens to it. After I do the multiplication, when I combine like terms, a negative 4x and a positive 4x are going to cancel each other right out of the picture. I'm going to have no x's left. I will still have the x squared, and I still will have the negative 16, but the 2 middle terms cancel each other out of the picture. So down here, what's left over? This is also a special case you need to know about. The x squared is a perfect square because x times itself gives us x squared. The 16 on the end is also a perfect square. The subtraction in the middle, of course, is called giving us a difference. So this whole thing together is called the difference of squares. That's when I have 2 numbers that are perfect squares being subtracted from one another. This is still a quadratic since I have an x squared, but it's a special case where the two middle terms canceled. So when I'm factoring the difference of squares, I need to keep that in mind. This is still a quadratic, so I can still break it down to two binomial terms, but the two middle terms are identical except for sign, so it's not going to show up in my quadratic expression. So let's take a look at what one of those would look like when we're factoring it. So here I have the difference of squares. This is a type of case that you might run into. 9 is a perfect square because it's 3 times 3. X is a perfect square because it's x times x. And 49 is a perfect square because it's 7 times 7. So before I can use this process, I need to make sure that everything is a perfect square. Make sure they have no common factors, right? We're not going to use this process if I have a greatest common factor involved. So first, the 9x squared breaks down into a 3x times a 3x. Remember, they have to be identical or this isn't going to work. The 49 breaks down into a 7 times 7. When I make one of these addition and the other one subtraction, I have my two factors. The first terms will give me the 9x squared. The last terms will give me the negative 49. And the middle terms, the inside will give me 21x. The outside will give me negative 21x, and those will cancel themselves right out. Is that going to be the same as 5y squared minus 45? Is this the difference of squares? Can I factor it the same way? The answer is a big no, right? 5 is not a perfect square, and neither is 45. So I have to factor this differently than I did that last one. We can still factor this quadratic, it's just going to look a little different. If I have a quadratic that doesn't have a middle term, I need to look for greatest common factors. Make sure that you've watched the greatest common factor video before you watch this part. So 5 and 45 can both be divided by 5. That's going to be my greatest common factor. So I'm going to pull a 5 outside of my equation or my expression. If I divide the first term by 5, what's going to be left over? We're going to have a y squared, right? If I divide 45 by 5, what's going to be left over for my second term? A negative 9. This is almost completely factored. But can you see something in my answer? Maybe something that we just talked about that we can still factor a little further? I have the difference of squares in my parentheses. So I need to factor this a little bit more. First of all, that 5 that's outside of the parentheses is still going to stay there. But my y squared minus 9, my difference of squares, is going to be broken down into two binomial factors. The y becomes y times y. The 9 becomes 3 times 3. 1 plus, 1 minus, so that my middle term cancels. And now I'm completely factored. Always be on the lookout for difference of squares. They'll pop up all the time. Let's take a look at one more example. Here's a trinomial quadratic, except right now my leading coefficient is not 1. So I can't look for factors of 32 that add to negative 16. That's not going to work in this case. But I can look for factors that they have in common. Is there a number that will go into 2, 16, and 32? You bet. I can pull a 2 out front, and then I'm left with an a squared. 16 divided by 2 is 8, and 32 divided by 2 is 16. What's inside the parentheses is a quadratic with a leading coefficient of 1, and now I can factor this further. I can look for factors of 16 that add to -8. So my first job to tackle is finding factors of 16. I can use 1 times 16, I can use 2 times 8, or I can use 4 times 4. Are there any of these factor pairs that will add to -8? You bet, that last one, right? The -4 and -4. So I'm going to break up my trinomial into the 2 factor pairs. The 2 is still out front, and now I have a minus 4 times a minus 4. This is completely factored now. There is a way that I can write this a little differently though, right? Since a minus 4 times a minus 4 is the same, I could actually write that as a squared. But either way is correct. Always be on the lookout when we're factoring for, first of all, greatest common factors. Anything that you can pull out from every term and put in front of a set of parentheses. Be on the lookout for difference of squares. Like I said, they'll pop up all the time. And quadratics with a leading coefficient of 1. These are all things that you should be able to do now, and we're going to use those all on our next assignment. Write down any questions that you have. Make sure to bring your notebook to class, and I will see you there. Have a great day.